Let's go and solve one of the interesting problems in the grid. And I really, I saw lots of the interviews, people ask grid problems, and we can play as interviewer actually. If we have a grid, we can add it, as much, we can add, lots of, the requirements and constraints in the grid to make it complicated. But, if you know the basic algorithm, it's not hard. If you know the basic algorithm, you will be able to write any, you will be able to solve any problem in the grid problems. Only maybe you will need to write more lines of codes, but the structure is exactly the same. So the previous problem, actually, we learned, how to apply BFS over binary tree. But when we have grid or graph, but right now I want to focus on grid. But grid and graph are so similar to each other. The problems are so similar, only implementation is a little different. But again, the structure is exactly the same as the BFS for trees. But we have one more item in when we do the grid, and you will see right now how we will handle that. Any question? Okay. So let's say, let's say we have a grid. This is the question. Let's say we have a grid or table, and the values are 0 and 1. Let's say I have 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, and 1. Okay, we have a grid. And let's say our indices are 0, 1, 2, 0, 1, 2, 3, 4. Okay. And the question is find, and actually, let's say, I want to go and define the problem in a formal way. So the given is actually is a grid. This is a matrix or grid, whatever, the term is not important. It can be, we can say matrix or two-dimensional array or grid. And given we have a source node, source cell actually, and also destination cell. So I'm naming, all of these guys cell. The source cell, we need two values, right? So it will be source row and source column. So these are our inputs. These are our assumptions. And the destination is dr and destination row and destination column. So we have a source inside of this grid and destination. And what is the objective of the problem? Find the length of shortest path from source to destination. Okay, so let's say, for example, this is our source and this is our destination. And there's another assumption, I didn't talk about it. We can only cross, pass only the cells with the value of 1. Zeros are, you cannot enter the zeros, right? Zeros are, let's say, sometimes in the problems they put X or anything. Any character which is not, depending on the definition of the problem. So we can only, also there's another, even so, we can only enter the cells with value of 1. So zeros are not, we are forbidden, it is forbidden to enter the zeros. So for example, for this problem, if we solve this manually, actually we have only one path in this problem, but and this is the path. So, and the answer will be 1, 2, 3, 4, 5, 6. So again, the length, depending on the definition of the problem, it can be number of hops or number of the nodes. If we say the length of the shortest path let's say this is number of the hops or number of steps, 1, 2, 3, 4, 5, 6. So we will return 6 for this problem, for this assumption, right? And that's it. You know, this is the problem definition. We want to go and solve this. You know, using the BFS approach, we can solve this also with BFS. But the reason I'm talking about this as a BFS, because the BFS will give us, you know, the simpler and more optimal. Because whenever we talk about the shortest path, when we talk about the shortest path, most of the time, BFS is the base candidate to solve the problem. But I will show you maybe today or the next meetup, because, you know, we will have every week. I can, you know, have, you know, the consistency between, you know, the sessions. I will, because, you know, before I had only every 2 weeks, but, you know, because now, you know, we will have every week. We will keep going in the, you know, they will be connected to each other, you know, the meetups. And maybe the next session I will, because we have some problems, the requirements, you know, the objective is finding the shortest path, but, you know, DFS is the best solution. But for this, because shortest path is shortest number of hops or number of steps. If it is shortest number of steps, definitely BFS is the best approach. And the reason why we say the BFS is the best approach, I want to again review the BFS in the binary tree. In the binary tree, we said we will put, you know, the first element, which is root, in the queue, and then add the next or children. Let's say we do here the same way right now for this algorithm. I want to put the first element, which is 0 and 0, right? I want to put in the index 0 and 0. This is my initial, which is my source. And this is actually my queue. I want to pop this. And what is the next elements based on the definition? Actually, we want to find the neighbors, right? In the binary tree, the next elements were, you know, the children, but right now are the neighbors. And there is another assumption here. Let's make it a little simpler. We can have move to only left and right and up and down. We don't have diagonal, you know, movements. Okay. So what is the next elements of the elements 0 and 0? I mean, this elements. We can go only for the 0 and 1. So we will we pop this and, you know, push the next elements. Let's say, because we want to calculate counts, right? We want to calculate the length of the shortest path. Let's say I push, you know, another variable here, which is 0, is count. Initially, the count is 0, right? So I pop this. What is the next neighbor? Valid neighbor is 0 and 1. And because I pop this is 0, right? I will increase by 1 my count or the length, right? So right now I'm in this cell. Again, I will pop this and push the next elements of this. What is the next elements? Is only this guy and this guy, the valid neighbors, right? So I will push, you know, 0 and 2 here. And if I go there, you know, 1 plus 1 will be 2. So this is actually the count, you know, this is our unit count variable, 0 and 2. And also I want to push, you know, the next element, which is 1 and 1. And count will be 2 again, because we pop this guy. Based on this guy, we want to find the neighbors of 0 and 1. The neighbor of 0 and 1, we have 2 neighbors, 0 and 2 and 1 and 1. These guys are, you know, the valid neighbors, right? So again, we will go and pop this guy. And now I'm here. What is the next valid neighbors of this guy? I don't talk about, you know, because we can go left also, because we already seen, you know, the 0 and 1, we don't want to add this, right? We shouldn't add, you know, any cell that we already visited. So I'm popping, the 0 and 1, and my count is 2 right now. 0 and 2, actually, 0 and 2. I'm popping this guy. What is the valid neighbors? Only is 0 and 3. And the count will be 2 plus 1 will be 3. Okay, that's it. And we have only this guy. And let's say now if we will pop this guy 1 and 1. What is the next valid neighbor of this guy? Is only this one, because we can have only diagonal. We shouldn't. We don't have any diagonal, movement. So the next element will be 2 and 1, and the count was 2. I will increase by 1. Will be 3. Okay, and 0 and 3 pop. Do we have any valid neighbor for this 0 and 3? If we go right, we don't have it. Is 0. Down, it is 0. Left 1, we already visited that one, so we don't have. So we don't need to push anything. So only we will pop it. And now it's time to pop 2 and 1. 2 and 1, I want to pop this guy. And what is the valid neighbors? The valid neighbors of this guy is, 2. Valid neighbors of this one is this and this, because we can go left and right, and they are not visited before. So let's do here. So 2 and 1, the next neighbors will be 2 and 0. 3 plus 1 will be 4. And also another one will be 2 and 2, 4 for count. Okay, the next element, 2 and 0 popped out. Do we have any valid neighbor for 2 and 0? So we don't have anything in the left, we don't have any in the bottom, right? Right, already visited. Up, we don't have things, so we don't need to push anything. 2 and 2, we will pop the 2 and 2. So now we are here. 2 and 2, we will pop, and what is the next elements? The next valid neighbor is only 2 and 3, right? So we'll have 2 and 3, and 4 plus 1 will be 5. Now we will pop this guy, and we will pop this guy, and we will add the other one, which will be 2 and 4. And the count will be 5 plus 1 is 6. And this is the destination. We reached the destination. Whenever we reach the destination, we will return the count. Whenever the next time I will pop this guy, and I will see that the node is this destination. So I will return count, which is 6 right now. Let's say the destination was this guy. We'll say, the destination, the destination row and destination column was, 1 and 1. So with BFS approach, we will go 1, 1. Whenever we reach this, the cell of 1 and 1, we could return that. We don't need to parse or traverse whole, the grid. And this is the power of BFS, because we go 1 by 1. This is really conservative method. We go 1, and we check all of the neighbors, the 1-hop neighbors, and then again we check all of the 1-hop neighbors of all the our neighbors. And whenever we reach the destination, definitely we have the shortest path, because we go 1 by 1. But if we go DFS, we have to go all paths. At the end, we have to find a minimum length. We have to find all paths using the DFS, because DFS is recursive, and we go only, let's say all of the right paths to the end, and then, and then right down, it is recursive. And because it is recursive, we need to check all paths. At the end, we have to find the minimum of all of them. But in BFS, actually, we are populating the minimum path, minimum length in our queue. Any question about the approach? I want to go for implementation, and then we will extend this problem, because this is one of the really popular problems in the coding interviews. Do you have any question about the approach? Okay, so let me check everyone, I don't have any feedback. Sometimes I feel, okay. Okay, so as you can see, again, we have a queue, but instead of, pushing only root value that we did, in the binary tree, we need to push, the row and column number and also count. And we need to add also the count in the queue. And, but also the neighbors or the next elements are different here. In binary tree was only, the children, but right now we wanna add the neighbors, the valid neighbors. Let's go and write the code, and you will see how it is, really similar to the previous code. The structure is exactly the same as each other, but we have a little more, coding here. So again, first of all, I wanna go and, import from collections DQ. As I said, DQ is a double linked list, and we use this as a queue here. And we want to define a function, shortest path. Len. So we have a grid, we have a source row, source column. Also, we have destination row and destination column. So we have, these are our inputs. First of all, I want to extract the dimension of the number of rows and number of columns. So let's do that. Rows will be equal to the number of rows will be len of the grid. And the grid is, the list of lists. Okay. If we have the len of, let's say we have something like this. If I, these are number of rows, right? If I say len of grid, it means, number of rows, and the columns will be len of grid 0. And I'm assuming here, the grid is not empty, but, we can, check it actually before, doing the grid 0. It is more professional, if we do that. So we have rows and columns, the number of rows and columns. And then, the first thing in BFS is define our queue. The queue is a DQ. And also, do you remember we talked about the count? The initial count is 0. And also, if you remember, we talked about, let me append the first element. So the queue, now we want to append the first element inside of this guy. So we want to append in the queue. So we want to use a list or array. And we want to go the source row, source column, and count. Okay. Actually, we want to have, because as you see here, in the example, we need all of these guys to find. We need source row and source column to calculate the neighbors, and count to calculate our metric, the objective of the problem. So that's why I'm adding a list that's or an array that contains all of these information. And initially count is 0. Also, we need to have a seen or visited, matrix. As you know, we said in order to find the valid neighbors, we need to know if we already visited a cell, we don't need to visit it again. If we don't control this guy, we will have an infinite loop. Yeah, our while loop will not be finished, right? Because we will have some loops over there. So that's why I wanna define a two-dimensional array seen to keep, that if we have visited or not. So for this guy, I want to define a Boolean, false or true, or you can use 0 and 1, doesn't matter. false for, let's say, X in range columns. So I created here right now one array, one list with the length of one of these guys actually. I created this guy. Also, I want to repeat this for number of rows. And actually, you can, use this in your language in different ways, but Python, actually we do a little, really compact in range. Oh, sorry. It's rows. Okay. And we have this guy here. So now we created a scene, I don't want to focus only, the syntax. This scene is an array with the number of rows and columns. Initially, all of them are, false. Okay, all of them are false. Whenever we visit any cell, we will update, the true with, we will make the cell true. So we have the scene, and right now, actually we visited, the root, right? Because we added, actually not root, the source. We visited the source and we added, appended in the queue. So the first thing is we have to write scene source row, source column should be true. It's because we visited that. So whenever we add or append any node, any item in the queue, we have to make the scene true. And now it's time to, it's time to go and write a while loop. So as you can see, again, similar to the previous problem, which was binary tree, we created a queue. Only thing, we created a queue and appended the first element in the queue. Only extra thing is seen or visited, matrix in this problem compared to the previous problem. And now let's go and write the while loop. While queue. Again, what is the first step? Pop the first element, right? And I know that if I pop the first element, let's say I'm writing in a queue that pop left, I know that inside of this, every element is a list. I can put, in Python, all of them in, let's say, source srsc and count. I'm directly, putting, all of that list, putting these variables. Okay, so we pop this, and then it's time to add the neighbors, right? Before that, we have to check, maybe it is the destination, right? So maybe the question is find the shortest path from, the source node to source node, right? So that's why, we have to, whenever we pop, maybe this element is the destination. That's why I want to write, SR is equal to destination row and source column is equal to destination column. It means that right now, we have, we reached the destination. So we will return count. Okay, we will do that. But the next part is to, define our neighbors. So what is the potential neighbors? I want to, first, define my potential neighbors, and then I will check inside a for loop which one is, the valid neighbors. Right now, that's why I want to define a potential neighbors all neighbors, right? Let's say we want to create, an array to add all of the possible neighbors. So I want to create a, it can be array, it can be, a list, it can be a set, doesn't matter, here it's really, it's not really important. So let's say I want to add, all the candidates. So if I'm here, let's say I'm here, let's say I'm in this node, I and J. I have 4 candidates, right? This guy, this, and this. So how can I, populate, write all those guys? I want to start with the top, this guy, the top one, right? And now we are SR and SC. So if I want to go to the top neighbor will be SR minus 1 and SC. Right? This is one of the neighbors, potential neighbors actually. And I want to go to the right neighbor. Right neighbor will be same row, but the column is one more, okay? And also the bottom one is, this row plus 1, but the column is same. And the left one is same row, but the column is minus 1. The reason I'm, writing this way, I want to show you the structure. You can't do really, really dirty code, but you will see that how it will help you to handle the really more complicated even problems. So after we pop the element, we are checking, this is updating the outputs. You remember I said, we should do something regarding the outputs, right? Right now we check if we reach the destination, we have to return it. And then we will update, we will find potential neighbors. We didn't have this, extra step in binary tree because, it was really simple. We know that the left and right are the potential neighbors. And if you remember, we checked if they are not none, we should add, the left and right. So left and right was, the potential neighbors, but we needed to check the if they are not none, we needed to add. So right now, we have this guy, and then let's go and traverse whole neighbors and check if they are valid, append in the queue. We want to append only the valid neighbors in the queue. So that's why I want to go and write for loop R and C, row and column, in potential neighbors. So if I go over these guys, so the first condition, row should be between 0 and rows, right? Number of rows, 0, and it should be between 0 and number of rows. So I will say if R, which is the row of my neighbor, is less than rows and greater or equal to 0. Okay, but if you are doing in other languages, you should do you should write if R is greater or equal to 0 and R is less than rows. In Python, we can write all of them in one comment. And in the second, important is column. We should check out our bound conditions, right? And the column should be also again greater or equal to 0 and less than columns. And also we need it is it means the cell is inside of the cell. For example, if we are in this cell, the top neighbor is not inside of the grid, so we shouldn't add in the queue. And in the next step, we have to check if it is 1. The value of this should be 1. R and C, the neighbor should be 1 because we cannot enter the 0 values, the cells with the value of 0. And also it shouldn't be visited before. So I will write the if I'm also seen at R and C is false. It should be false. Okay, so this is my condition. The validity, this check the validity of the neighbor. Neighbors, right? So if it is valid neighbor, it's time to add this in the queue. So let me write this part, as inside of this guy, q dot append. I will append the neighbor, which is my current neighbor, right, will be R and C, but I have to increase count. Do you remember? You know, we had a count. Count plus 1. Okay, so as you can see, now we are populating all the neighbors. If they are valid, we add the neighbors in the queue and we increase the count. And whenever, you know, we add in the queue, as I said, whenever you add the queue, it means you visit it. So you have to update the scene. It is really important. If you forget this line, you know, and it is really common mistake, you know, for most, you know, people, they forget to update the scene. So you will have this, and we will do all of these guys whenever we reach to the destination in this line. And, you know, actually this part is really important also. We will go there. Whenever we reach the destination, we will return the value, return the count. Let's say we didn't find, you know, the destination and we finished and the queue is empty. We will return. Let's say we return -1. It means that, you know, we didn't have. You have to discuss, you know, you have to ask, you know, your interviewer. But, you know, -1 is a really reasonable, you know, answer, because -1 is doesn't mean, you know, because we want to return the shortest path, and -1 doesn't mean any valid value, right? So you can return none, or you can return -1. I think the -1 is better because we want to return, the type of our return should be consistent. So as you can see here, you know, this is our code. And I try to write the code, you know, for you guys as really as in a structured, you know, way. So again, as you can see, we have we are, you know, defining the queue and adding, you know, the first element of the queue. In the while queue, we pop the elements. This is the first stuff, we talked about it. Update the output. Here is the checking, you know, maybe if we have, and adding the neighbors. But here, adding the neighbors is a little, because we have to check the validity. So that's why, you know, we, you know, have the potential neighbor. You know, actually we could do this inside of the for loop, but I think in this way, your code is much more cleaner. And if you run this, you know, actually I will update, I will share the link of the source codes, my own codes, in the meetup. And you can go and, you know, see, you know, that even in the source codes of these problems I'm solving in the meetups. And also in even the social media, you know, I will share, you know, but the social media of, you know, my website and my, you know, social media website, and you will find, you know, really useful, you know, the contents and the problem solvings.